Lurking in the darkness of the cosmos, the two Voyager spacecraft are the farthest man-made objects in space. Yet, even after more than 4 decades, they have been exploring the cosmos and beaming back data from interstellar space. Today, at 23 billion kilometers, Voyager 1 is the most distant spacecraft from Earth. Even signals take more than 20 hours to get there. But have you ever wondered what has been powering these spacecraft for so long? What exactly has been their constant source of energy for so many years? Whenever we think about powering a spacecraft, a normal battery is the first thing to strike our minds. If you scratch your head a little more, the second answer could be solar panels. These two are the common sources that can power most of our gadgets. So why wouldn't these two work for Voyagers? Well, yes, they can work, but there's a small problem. As you know, the achievements made by Voyagers are grand. Voyager 1 became the first spacecraft to enter interstellar space in 2012. To travel such long distances, a spacecraft needs enormous power, and if you want to supply this power via regular batteries, you need a lot of them, which will make the spacecraft extremely bulky. Coming to solar panels, it's a good idea, but not with the current technology that we have. Solar panels become inefficient at a certain distance from the sun. Until now, the most distant uses of solar arrays have been in the case of Juno, which is a probe designed to orbit Jupiter. Moreover, Mission Dawn aimed to explore the protoplanets Vesta and Ceres, and the well-known Rosetta mission, which visited a comet, was also powered by solar panels. But when it comes to Voyager, the distance it is supposed to travel didn't fit in the present range of working for solar panels. So, what now? Well, scientists at NASA had thought about Voyager's power source long before they launched the spacecraft. And the source was just like a battery, but one that works differently from the regular batteries. This battery is what we called a radioisotope thermoelectric generator, which is more commonly known as RTG. To be precise, RTG is an innovative method used for powering space probes for much longer trips. And you would be surprised to know that Voyagers aren't the only ones to have been powered this way. Instead, this method has been used for more than 24 space probes over the years. Famous examples include the Cassini spacecraft sent to Saturn and the New Horizons probe to explore Pluto and other objects beyond the dwarf planet. Coming to RTG's working, it operates like a battery, but a bit differently. I feel it is much better to say that it's a nuclear battery. This has definitely given you the idea that an RTG uses nuclear fuel. But how? It is known that whenever a radioactive element decays, it releases several particles. But along with these particles, radioactive decay is accompanied by an enormous release of heat. And this heat is the byproduct that comes in handy in powering spacecraft like Voyager. So how is this heat converted to energy in an RTG? The answer is a thermocouple. A thermocouple is a device that produces a temperature-dependent voltage. It comprises 2 dissimilar metallic wires that are joined together to form a junction. When the junction is heated or cooled, a small voltage is generated in the electrical circuit of the thermocouple. The main component of the whole RTG thing is a container containing the radioactive material called the fuel. When the radioactive material decays, it produces heat, which heats one side of the thermocouple, one of the metals. On the other side, the cool temperature results from the ambient temperature and deep space, which is cold. It's just a simplified version of what happens. In reality, these things are much tighter under control. Even choosing the radioactive fuel for an RTG is a crucial task. Many factors need to be considered while making the right choice. And first and foremost, criteria of the selection process is the half-life of the element. An element's half-life tells us how long it takes for atoms to undergo radioactive decay. This means that we need to choose a material with a longer half-life to rely on it for a longer period. Secondly, an element should have the ability to produce high-energy radiation while decaying and should tend to produce radiation decay heat. Apart from this, there should also be large heat power-to-mass ratio. The original list of radioactive isotopes contained 1,300 members, but looking at the discussed requirements, only 3 elements are most commonly used, and these are plutonium-238, curium-244, and strontium-90. Now, if we talk about Voyager 2 specifically, it works with plutonium-238. Collectively, the RTGs supplied the spacecraft with 470 watts at launch, and those have every 87.7 years. Why 87.7? That's the half-life of plutonium-238. However, nothing lasts forever, and the same is the case with the power supplied by RTGs. So it's crucial to manage the spacecraft's resources, and NASA has done that incredibly well until now, saving already a lot of power. They turn off systems when not needed and permanently switch off those systems with no chances of improvement. In time, other instruments were turned off too, but still, Voyager 2 is expected to be no longer able to power any instrument by 2025 or a bit later. And same is expected for its twin as well. The Voyagers might be able to send weak signals, but we can't know that for sure. Even after the twins will no longer send signals back to Earth, they will continue their travel through the vastness of space. And eventually, after 2036, both probes will be out of range of the deep space network, diving into a sea of eternal silence.